Hi everyone, thanks for joining us today.
It does sound sophisticated.
Sophisticated, yeah.
With the ACE community for 3 years now.
Actually outlined everything.
Something that we find in the society.
First, talk about the problems that you're trying to solve.
Hi everyone, thanks for joining us today. We are here with another episode of Deep Random Talks, and we are going to randomly talk about brain and knowledge and other things that are contained in our brain as we do all the awesome things we do. So today with us we have Shady, who is building something very interesting that we're very excited to tell the story of that to you. And my awesome host as usual, Carla, who is traveling in Italy these days. So what's happening with you, Carla?
Yeah, so I just made my way down to Calabria. I'm here at this really nice hotel. Got some good food. Weather is not so great today, but I can't complain. I am in the south of Italy right now, so.
Yeah, you don't get to complain.
Life is good.
Even if things are bad, you don't get to complain in south of Italy.
Exactly.
And Shady, thanks for joining us today. Tell us a little about Shady. Who's Shady?
You bet. So my name is Shady. I'm a neuroscientist. And over the past 2 years, I've been really interested in the interface where software meets science. And specifically, how do we really leverage the tools that we have for coordination on the internet to think about how we can come together and solve really hard, difficult problems. And so I think this is something that probably bridges beyond just pure science, right? But maybe general problem solving in society. But I think kind of starting with, maybe neuroscience, my background, and figuring out if we can wrangle everybody together there is a good place to start.
100%. So usually in Deep Random Talks at the beginning as an icebreaker, we talk about what we were drinking. But a very organic thing that happened when we were doing the coordination call for this session was that we started talking about our favorite parts of the brain, essentially. So now instead of what you're drinking, we're going to ask that question. So let's start by Carla. What's your favorite part of brain?
Yeah, so I'm curious if I'm getting this right, but I believe there's the specific brain area that's involved in recognizing faces, and I think it's called the gyrus fusiform or something like that. I may be completely wrong. Is it right? Yes. Okay. So that's my favorite brain area.
Full points on the advanced neuroscience course. There's a great book by Oliver Sacks called The Man Who Mistook His Wife for a Hat.
Yes, exactly.
And so all kinds of really funny things can happen with that. There's some interesting backstory with FFA we can maybe get into at some point.
Very interesting. That's one of the most phenomenal books that I've read. Like every single page of that book, I was like, whoa, this thing that I take for granted is really happening here, which is fascinating. For me, the ability to tell stories and, the imagination that we have, creating artificial realities is very fascinating.
The hippocampus is definitely a part of that story because it's important in episodic memory recall. So definitely on the part of the storyteller and maybe on the story listener as well on their part, because they're forming new episodic memories as they kind of emulate the story and try to imagine exactly what went on and what happened. And so Yuri Hassan's lab found that the storyteller's brain activity was synchronized with the story listener, and the more engaged the story listeners were, the more synchronized they were amongst each other. I feel like it's really hard to pick a favorite because they're all kind of important or interesting or quirky, but I think...
This sounds like a parent talking about their favorite child.
In a way, yeah. So when you've spent, I guess, as much time as myself as a grad student staring at MRI images on console screens, you'll feel a sense of kinship with a lot of these little squiggles, black and white squiggles. But mine, I'd have to say the most I've spent staring at is the basal ganglia. It's a really, really cool area. It's preserved across many different types of species, and it's implicated in all sorts of cognition, right? So it's composed of a bunch of different subnuclei, and it's a mess. It's an absolute mess. It's reticulated, right? So that it has kind of this meshwork of neurons that are overlapping, and it's been really kind of important in reinforcement learning. And more recently, I think of interest to the audience, this one professor Brodvinick, I think, over at Princeton, then he went over to DeepMind, really kind of pushed the basal ganglia and the prefrontal cortex as being involved in this loop called meta-reinforcement learning, where, it's like answering kind of the question, who teaches the teacher, right? How do you set examples for reinforcement learning? And the basal ganglia and prefrontal cortex kind of, their kind of loop allows for that sort of relationship to emerge over time.
All right. Okay. So maybe let's move from the topic of brains to the topic of your work, because that's also a very interesting topic. So, maybe a bit of backstory. So Shady and I met, I think it was in Amsterdam, right? So this was we had a conference there with many people from the DeSci community. We had like a full DeSci day, booked out like a theater, and everybody got to present their projects and everybody got to meet face to face. For me, this was the first time meeting DeSci people in person. I think you guys had already met before in Denver.
If I had to kind of, really quickly say why I'm doing what I'm doing and not off, driving an MRI truck around the rural parts of South or North Carolina, scanning people, is that I'm building the tools that I need to best do the research the way I think it should be done, or at least the way it should be done, right? Generally. So what I'm focused on specifically are solving data engineering challenges for science. This is kind of how we got started, dealing with how do we, how do we put together infrastructure and rails for seamless, painless, large data set sharing and collaboration. And secondly, how do we empower web native communities through the browser, right? So, scientific data is like, it's heavy, it's monstrous, it's complex, and you need all sorts of specialized systems just to like visualize the basal ganglia at like 100 micron resolution, right? That's a massive image. So, how can we take advantage of the most recent innovations in tech infrastructure and server infrastructure and software, and be able to deliver a portal to the knowledge that's being accumulated and digitized through a web browser? And so data sharing is a strong part of that. It's a very important part of that. And as I've fallen deeper into the rabbit hole, I've realized that coordination around knowledge is really kind of the question that I'm trying to tackle. And
okay, so maybe for some context, you said you fell down the rabbit hole. What were you doing before you fell down this hole? Like, what was outside?
I was finishing up a longitudinal neuroimaging study. So about in 2014 or so, 2015, I started working on an adolescent neurodevelopment study where we were tracking kids from ages 11 to 13 into adulthood. And so we had 4 time points that we collected along the way. I came into the lab a little bit, after the study had started. So I jumped in right towards the middle of the second time point, and I got to see kind of how this, how this effort was ongoing, and just how many moving parts there were when you're trying to collect, this really complex data set and in collaboration with other institutions at other universities. So when we finally got to the finish line, we got that 4th time point, we got that last set of MRI images, and we were able to develop these growth charts that could tell us a little bit about the brain age or the cognitive age of a child as they're growing, and contrasting that against the chronological age, right? So where chronological age is, the time you're, since your birthday, since the year of your birth, and biological age is perhaps more the developmental age, perhaps you're developing more or less quickly than your peers. And so it was really important at that time to generalize or extrapolate our results to a wider population to validate that. And due to the size of the data sets and the level of statistical kind of criteria that we needed to meet, we had to incorporate data from University of Melbourne in Australia and at the University of Rio Grande do Sul in Porto Alegre. And so one of the big issues there was how do we share data in a collaborative cloud-based environment while also kind of getting around some of these regulatory concerns of, Brazil versus Australia versus GDPR in Europe, for example. And at the time, I was a participant or like a really active member in the brain hack community, which in all ways is a decentralized science community, right? It's just a bunch of grad students and postdocs and basically people who just don't like being closed up in their labs and only working with their, in absolute secrecy with only the PI as the head honcho there. But really collaborative kind of culture that had formed over the past 10 years with folks like Cameron Craddock and Sattar Ghosh and Russell Poldrak really kind of waving the banner at these elite universities and saying, hey, it's okay, like you guys can work out in the open and it'll be fine. We'll all progress together. And so that's where we really dove into IPFS and interplanetary file system. It sounds crazy, right? Being able to share data sets from peer to peer without going through this third-party server.
When I think about collaboration on complex things, it reminds me of what GitHub did for source code. Because, source code is generally, and software in general, is fairly complex. And, in the world prior to GitHub, people did collaborate on a smaller scale, within the same company and probably, where they were sharing devices. And, one way that I like to talk about what we are building is that, we are building GitHub for knowledge because, knowledge is very complex and, you could imagine doing the same type of things that GitHub did for source code for knowledge. And listening to you, it makes me think, you're almost, or at least the beginning of the story was that you wanted to create GitHub for complex data sets.
Well, yeah, actually at the beginning, we just really wanted to share data across peer-to-peer. And funny that you bring up GitHub. So GitHub runs on Git, which is a funny named software library invented by Linus Torvalds from the guy behind Linux, which allows us to actually use cryptography to version control data, right? So or in this case, lines of code. So in GitHub, what you do is you assemble what's called a Merkle tree of the history of a folder or a directory structure. And then when you add something to the Git index, what you're doing is you're computing a checksum. So you're taking that piece of code and you're running it through a one-way function, and you're generating what's called a digest or performing a checksum that tells you that the content of that file corresponds to this unique string that uniquely labels it. So it's great for code because you can kind of implement these other sorts of flows on top of it and figure out from one version to the next how do two documents differ. But when it comes to data, which is stored in all sorts of funky, strange, hexadecimal, bytes, all sorts of different representations, it's not as easy to version control data. And that's what science runs on. It's not code, it's data, right? So there is some tooling out there. So there's an open source project run by this famous guy named Joey on the internet called GitNX. And he's basically rewritten Git version control for binary version control. And on top of that, a bunch of neuroscientists built DataLad. And DataLad basically just streamlines a lot of this stuff and makes it possible for anyone, anywhere to do a scientific experiment and then publish it to a distributed archive, right? So where anybody can use GitHub in the same, they can publish to GitHub or an Amazon S3 bucket or anywhere really, and be able to let other people clone it, reproduce it, generate derivative works, branch it, fork it, modify it, do more science with it, right? So the problem with DataLab, though, is that, again, it's relying on Web 2 infrastructure. And by Web 2, what I'm really saying is that Web 2 is like either personal servers that you're running DNS, static DNS for at the laboratory, for example, or an institutional server that might be behind a bunch of firewalls and other kind of requirements, or on like an Amazon S3 bucket. And the main thing is, if maybe Amazon might give you free ingress. They'll say, hey guys, you can dump all your data on here. We'll give you a really great discount. Maybe it's even for free. But what ends up happening is that data gets locked into it because Amazon charges egress fees. And so whether it's Amazon or a personal lab server or institutional server, for example, University of Melbourne, that their neuroscience institute during COVID completely shut down, and data that they had, not all of it was saved. So in Web 2, we have these issues of persistence of data. And we already have cryptography tools that can let us solve these issues.
You're saying there are some solutions-ish, but they're not great enough. And so you were at this brain hack or involved in this brain hack community and then aiming to build a better solution, right? So what was the initial idea?
And yeah, the goal really was to make it possible for derivatives of data to be version controlled based by their content. So, you could do a cryptographic checksum of the data and know, for example, if it is the data that was generated from an algorithm, an analysis algorithm, for example. And at the time, we dove into IPFS, and then after the brain hack, we realized that there's a much richer ecosystem governed by smart contracts and by things like, Filecoin, for example, really stuck out to us as these incentive engineering mechanisms, right? So Filecoin is fascinating. It solves one of these issues with persistence and a bunch of other issues too, by the way. But with persistence specifically, Filecoin, basically what it does is it abstracts spare storage space as a commodity, right? So anyone who runs Filecoin software on their computer, they can configure it to sell extra storage space on their computer. So anyone can store anything on their computer. And on top of that, they have a bunch of proofs, cryptographic proofs that are run on top of the stored data that guarantee things like proof of persistence, so that the data is always there and available, that it's available at like discretized time chunks, and that it actually passes regular validation checks, right? So that the sectors on a hard drive, if they go bad, for example, the storage provider could get slashed, right? And so what do I mean by getting slashed? Well, to participate in Filecoin, you have to stake Filecoin tokens. And then for each successful block that you're storing, you're receiving Filecoin rewards. Now that's pretty cool, but there's an issue here with Filecoin. And I think this is something that I realized really early on, is if you don't kind of put in some sort of guardrails, you might end up with kind of this runaway train where you have this, runaway incentive engineering mechanism where it's valuable to store data. And what kind of data are people putting out there? Let's go look on the internet, right? And you'll see that some of it's pretty suspicious, maybe not the best content out there. Maybe illicit content, maybe weird kind of stuff, maybe a lot of cat photos. And so could you imagine like this Nick Bostrom sort of situation where instead of a paperclip machine, you have like this storage machine that's just storing tons of selfies and pictures and iCloud backups, right? So Filecoin Plus was invented as an incentive engineering solution to this, where the rewards were shifted from those that were storing your ordinary cat pics to those that were storing valuable data that was notarized by a board that said, hey, temperature data, geospatial data, knowledge data, brain imaging data is valuable to our society. So this incentive economic machine should subsidize that. And so what we ended up doing was building on top of Filecoin and procedurally indexing the DataLad index, which is about a 500 terabyte index that's publicly available, and constructing basically an automated backend pipeline that extracts metadata, that extracts the version control out of that, and archives it on Filecoin, pins it on IPFS. And so we wrapped this all up and we called it a data commons, a decentralized data commons. And the purpose of this really is to make sure that there's a permanent home for scientific data that's been published either through DataLad or through the platform itself.
You did your PhD, along with it, towards the end, you were doing some sort of a hackathon where you identified a problem. And I believe in our coordination, you also mentioned that, I don't know if it was part of that hackathon or something later, that you got some funding and the initial idea was, can I create a DAO that solve this problem based on, what we explored in the hackathon. So you started exploring ideas around data wallets and data vaults and, as you say, data commons kind of ideas that you want to explore. But then, you started noticing the problem with the existing solutions, that there was no, control is probably the wrong word in a decentralized world, but, wrong incentive system to make sure that more valuable data sets get seen more, etc. And at this point, you started thinking, okay, how can we do this differently? And that's where sort of the core idea of the product you're building today was shaped.
Yeah. I feel like I can't continue without really pointing out a moment of epiphany for me, um, which is, so I did a lot of automation in the laboratory, right? Like taking data off the scanner, getting it ready, because there's a lot of manual labor that goes into it. And I was kind of obsessed with automation in the laboratory to the point where, I was wiring up iMacs all throughout, whatever facility I had access to, and putting them together into a SunGrid engine compile, basically, like a high performance compute engine, right? Like a supercomputer. So, and getting, putting GitHub and all this stuff together so that we had interns across the country or in different countries, like logging in and manually correcting and contributing to the work that we were doing. So, I'd always been a fan of automation, but I don't think I really grasped like what challenges large scale automation had to overcome in order to be like effective in production. I mean, all those projects that I did in the lab, they died after I left. Now, what's fascinating about this so-called mythical Web3, the thing I think that really distinguishes it from the technology we have been building before, is that Web3 it's a decentralized consensus machine that never stops running. Reality is appended one block at a time. And as long as somebody is running some software on hardware, that will continue going on. And, there's like all kinds of crazy estimates from, investors and the DoD of the Ethereum blockchain ecosystem, how it could even potentially survive a nuclear winter because of, where these nodes are being run and how much energy they have access to. So thinking about automation and life and what happens when you deploy something, not a platform, but rather a protocol that is parameterized around certain incentives or coordination mechanisms. And I quickly realized that, okay, we're putting this project together and we can just have fun with it. We can put the code out there. And if someone wants to continue the work, they can go ahead and do so. But there's an alternative if you're building smart contracts on Web3, which is you can compile. Your smart contracts are all open source, by the way, which is completely different culture shift from Silicon Valley with Web2 mindset, and deploy them publicly open source on the Ethereum blockchain, where they'll always live and anyone can interact with them at any time, as long as they can pay the gas fee to run computation on that server. So it was at that point that I realized, hey, like, if we're going to have a data commons and we've parameterized it for our unique, case for, the friends that we gather to solve this problem that interested us, that's, we needed to start thinking about how do we organize around coordinated governance or coordinated decision making, because maybe people want to add new standards to the data commons, or maybe they want to change the size of the chunks, right? Because maybe like technology changes over time. And how do you automate, or not even automate, but really make the ability to make decisions and change in the same way that, open source Linux software goes through today, but in automated permissionless systems? How do you empower that? And so that's where, we started really thinking about DAOs, these decentralized autonomous organizations, where you use cryptography to ensure that a particular address or identity in the community has some sort of permissions or rights to make proposals, to vote on proposals that then change the core code that's then updated in production and continues living on, kind of almost like a sentient piece of software in some ways, or maybe sentient's too strong a word to put it. And so that kind of really marked the shift, this epiphany of, hey, blockchain systems are, they're not just this one-time GitHub repo, but they're going to be persistent and live on in the blockchain's history as long as that blockchain is running.
And so this epiphany about DAOs and the power, the potential power they can have. What does that change about what you were building? How did it change the trajectory of your story?
Yeah, so once you go permissionless, all hell breaks loose. Absolutely all hell. And maybe this is a good thing if you imagine, like, I don't know, that you think that like the evolution of life is going to be synthetic and information driven. I don't know, who knows? But with once you make things permissionless, it kind of resembles an open ecosystem for any sort of adversarial behavior or exploitation. And specifically through bots, right? Through automation can be written in ways that are agnostic, as long as they're parameterizing some objective function of maximizing profit or whatever the objective function is, archiving cat pics, someone will take advantage of that system. So it became really important to us in these permissionless, data commons or marketplaces to verify identities of individuals that were participating. But it's a conundrum as well, right? Because a blockchain is persistent and immutable and lives on as long as the network lives on, and potentially forever, right, until heat death. But at the same time, you want to be able to prove things about a person, but you don't want that person to be kind of like held prisoner to the identity that lives forever on that blockchain, right? So this really delicate balancing act between privacy and basically security or trust and reputation was something that was really interesting to us. We thought it had a lot of power as well, because there was an opportunity there to kind of transcend what we thought of as academic credentials or identity or reputation in this Web3 setting, where your reputation was literally linked to this Ethereum account or address that you can pull up all the events or contributions or histories and build these really rich graphs of a person, right, or an agent, really, right? So that's when we announced another hackathon about just a year later, actually, at ETH Denver, and this coincided with the Decide ETH Denver event that we put on together with Foresight Institute and Smart Contract Research Forum, and met the wonderful guys from Decide Labs there too, as well as others building in the space. And so what we really wanted to do was solve this issue. How do we maintain anonymity and privacy while also being able to register accounts on chain so that we can gate access to free storage, for example, so make sure people aren't storing weird things. And so we started development on this project, and we put something together, won a hackathon prize from Harmony, and later we developed a prototype that we launched at ETH Amsterdam about a month later called the DeSci Identity Registry. And it was built on a protocol that eventually we ended up calling Holonym. And Holonym is a direct reference to Nick Szabo's article that he wrote in 1994, where he first coins smart contracts, and also the term NIM, or name, from Latin, I believe. And so, with Holonym, what we really wanted to do, and it's present in the name, right, is we wanted to create, basically our goal was to create a smart contract that lived on chain, that represented elements of the identity of the individual. And through this smart contract, any agent, it doesn't have to be a person, but rather any agent, can link other arbitrary cryptographic key pairs. For example, if you're a cryptography nerd, perhaps your GPG keys, right? Or perhaps your FIDO2 keys from your Apple Face ID, or maybe just like your Google account, or your, in our case for academic services, ORCID, right? Like your academic web login that lets you publish in journals. And so that's what we launched at ETH Amsterdam, although at the time everything was public. So if you're using the service, you're basically doxing your Twitter accounts, your ORCID, and all that good stuff, which we thought was fine at the time because we wanted people to represent their academic credentials and not keep that private. Since then, Holonym's kind of gone off from a DeSci focused track to focusing really specifically on zero knowledge proofs that preserve anonymity, while also kind of uplifting these permissionless systems that allow us to produce proof of X. And the case study that, or the use case that we're actually just finishing up right now, you can check out, there's a browser extension in the web store, is for Lobby 3 DAO. Lobby 3 is Andrew Yang's DAO that was spun out of Humanity Forward. And they have this really big issue where it's like, hey, we're a DAO. Anybody can join and throw money into this pot and we'll go support elections and do lobbying activities. Well, surprise, the US government has laws against anybody anywhere in the world participating in that sort of permissionless ecosystem. And so, we came to them with a solution and say, hey guys, here's what we have. You can prove securely and privately that you are a resident of the US using a zero knowledge proof. And we can go into that a little bit. But that preserves where you're actually from. So you can either have a logical Boolean that says, am from the US or am not from the US, and associate it with an Ethereum on-chain account.
Okay, tell me about zero knowledge proofs. Like, this is a big topic. It gets talked about a lot. And so, okay, my understanding, because I'm not from a technical background, all I get told is, so it's this computer science thing where there's information, but you can only ask a question into a black box, and the black box will only tell you yes, no, maybe, like the magical 8-ball from SpongeBob. And then nobody can explain to me like how that works.
I'll try my best. So zero knowledge proof is really cool because it unites zero knowledge systems, brings together many different fields of mathematics together under the umbrella of computer science to basically have an applied version of like solving for roots and like set theory and category theory and all of these, modular arithmetic. They all come together under this big umbrella to solve the problem of how do we prove things or prove knowledge of things without giving up any more information than what we decide we want to give up. That's the key of it, right? So you pre-allocate a statement that you decide you want to evaluate as true or false and present it to somebody or anybody really. And you don't want to really kind of give up any information beyond what's used to compute that Boolean. So a little bit more detail. Zero knowledge proofs, the way that they work is that you can, the basic core idea is that you can represent almost anything as a polynomial, right? And you can have, so in like numerical systems or like any systems theory sort of class, you might learn about different methods like Gaussian elimination or different types of methods for finding the roots of a polynomial. So what zero knowledge does is it basically obscures those roots in a way so that that true false statement will evaluate to those roots, and you can kind of make it such that it's very, very, not absolutely impossible, but very difficult to discover those roots unless you have existing knowledge of, say, perhaps, the independent variable, for example, that it evaluates to, right? So in a little bit more detail, basically what you're doing is you're taking some representation of data and you're encrypting it in such a way that you can still run math on it. So for example, if I take the equation 1 plus 2, right? Or maybe the polynomial like 3x plus y, and then I encrypt it into some hexadecimal representation or something wild, I can, depending on how I encrypt it, I can perform mathematics like expanding that polynomial or taking the derivative of, well, that's a little bit more extreme, but let's say it's simple things like addition, subtraction, multiplication, and then division is actually kind of complicated. But you can generalize it, right? And that's what like StarkNet and all these other technologies do, Starkware. So you can run math on this encrypted form and evaluate different representations or results from it without ever seeing originally what that expression was. And it's kind of similar to homeomorphic encryption and some of these differential privacy techniques, but it's not exactly the same. And at the heart of it is modular arithmetic. That's what you're really using there. I still identify primarily as a researcher. I love engineering cool solutions and diving deep into new technology and seeing how we could solve problems. And yeah, so I think there are some amazing potential use cases where we can make these permissionless digital spaces, protocols, nexus points for coordination among scientists that are publicly known, like Max Tegmark or Michio Kaku or whoever, or perhaps they're pseudonymous. And these are the guys that are perhaps calling out the science, right? Like Neuroskeptic. or I can't think of any right now, but over the 100 or so pseudonymous research identities that either have published or have some social media presence, or communicating science in some form. So I do believe that science can go in new directions once we've kind of cracked this identity components, and being able to allow people to choose how they represent themselves online can specifically open up kind of new spaces for collaboration and rigorous discourse, that in other ways where your tenure track application is dependent on, you might not be able to really kind of explore, to say certain things, or to propose wild ideas.
Like, I see the value in not necessarily sharing your identity every time, and especially when it comes to like critical discussions or something. And maybe I'm naive, but I feel like science should be a space in which that sort of discussion is encouraged, and we can do it with our full names, because I always feel like that's just a lot more accountability then. So if I say something and it's like me saying this, then I'm going to be careful in what I'm saying, not holding back intellectually, but just not attacking people, not, there's all sorts of bad content that people produce just because they're anonymous. Like, just look at Twitter, look at all of Twitter and you see.
In the case of Twitter and YouTube and these other Web2 platforms, these accounts are single use. They're throwaway accounts, right? Where you go on there, you say whatever you want to say, and there's really kind of no repercussion or penalty. I think when we kind of up the ante, again, blockchain is immutable for better or for worse. And I think on top of that, you can add all sorts of gating mechanisms for example, linking an ORCID account to gates access to a place of discussion, and where that history with that account becomes associated with your publication history, with your peer reviews, with your future matching. It's almost like a character that you've developed in an MMORPG, like a massively multiplayer online role-playing game. And sure, you can have that one character that runs around naked and spams everybody and tries to steal people's money. You're not going to get very far in that game. But if especially in the scientific game where collaboration and trust and relationships are key, those are the kind of incentive mechanisms that we want to empower. And like when you say, oh, we need our names, or I think that's I tend to also agree with you. However, if we kind of take a step back and look at the scientific papers that are out there, we don't really know that much about the authors. Their name could be anything. We just know that their name appears in context with other authors and other maybe we see them in a conference or something. But for the most part, especially by COVID, during COVID, I think this really hit home for me, is these strings that these descriptor strings that we put on there to say this person is that person. We only know it or trust it as much as the context that surrounds it. And cryptographically verifying that is a much more powerful way.
What you're describing is, brings up another question, which is, how do you ensure the continuity of an identity, right? Like you're saying that Twitter and, YouTube weird comments are usually from throwaway accounts with like 2 followers that are used for a week and then abandoned, right? So, but is there a way to ensure that, a person has a continuity? I guess some variation of reputation is what you're saying. Like you might notice a name, you don't necessarily associate it even with a face on papers, right? But that name, the continuity of name on papers that you recognize, is the thing that gives you the reputation, is the thing that gives you the trust that, okay, I should listen to what this person has to.
Really skimming the surface here, like once I think kind of going in a little deep, we'll run into a really challenging problem in computer science called Sybil resistance. And it's something that, the best minds in the world are working on, and there's really no clear, perfect solution for it. So a little bit of kind of random context, Sybil resistance is this property that a system or protocol might have against duplicated identities attacking the system. And so when we talk about continuity, what we're really kind of talking about is how do we link the previous, the history of an account with perhaps another account that might have been also shared that history or been by the same person. And so we're looking for things like proof of personhood or proof of uniqueness, which are non-trivial. And this is something we've been spending a lot of time thinking about as we're designing Holonym. And we think we have a solution that's not perfect, but that can solve the majority of most use cases. So what we do currently to provide proof of uniqueness is we generate a checksum of some document or supporting record that we know to a fair degree of reasonable certainty that it can't have been created by anyone else. So things like a driver's license or diploma or another issued state ID. So it sounds scary. It's like, oh, well, you're going to have to give up your identity to use these systems. But we do it in a zero knowledge way, right? So when that image is taken, it's kept local in the browser before it's pre-processed, encrypted, sent to an automatic verification system that has been audited to be compliant with these privacy regulations. The data is then deleted and a proof is generated and put on chain. So what that means is that you can never generate an identical proof and associate it with a new identity, because this is what blockchains are great for, because it's a single source, it's a reference source, because you can look on the blockchain and see if that hash, that that digest that we cryptographically generated from the content of that data already exists or not. And so you can kind of get around this issue, but then the weakness really is that record that you're using.
Definitely a lot of interesting questions to be asked, and I'm glad you're working on those. I'm sure a lot of people need better answers for these kind of questions going forward. And definitely all of these nuances that you're talking about are things that were not necessarily obvious on day one when you started working on. I'm sure you had different types of assumptions about what you're going to do, and the world that you were imagining was probably very different. So I want to sort of bring it there. Like, what are some of the other assumptions that you had at the beginning that ended up being incorrect, and how did you come to learn those?
Yeah, that's a really good question. So I think kind of going back to the data engineering problem, and we thought, I thought I was solving a problem for myself. Like, I had no idea what I was going to do with this data. Where was I going to keep it? And I thought that if I build it, they will come, right? If we do the math and show our work, people will recognize that, they'll see it checks out, and it'll work. That's not always the case. I think especially in science, where it's a messy social ecosystem. There's tons of complexities at the institutional, departmental, even lab level. And I think the one thing that I knew already but failed to really empathize, or I guess project into the general scientific universe out there, but is that scientists are tired. They're really tired. And if you're going to come up with them and try to convince them to use this new fancy, Ultra MX 1000 www.com, OpSci Commons, whatever, that's how they're processing it, hearing it. They're going to be like, oh, that's okay. I'm going to go put my hard drives in the closet where I always put them, because that's what works like enough times for me to keep going. So you need to have a really compelling kind of reason. We need to build a really strong relationship, and you need to build with these scientists, like literally holding their hand.
Yeah, I really empathize with the tiredness of scientists. So I get this a lot as well, trying to convince people of what we're building at DeSci Labs. And it's like, ugh, I have so much other stuff to do. Like, don't bother me. Leave me alone. I guess that's also a problem of its own in science. Like, why is everybody so tired? We need to do a better job in letting scientists do their job, I feel. But yeah, okay. So we've been talking for a while now, and I guess we're kind of at a time limit. We don't want to overgo. Okay, so you told us about your story. It changed a lot. It was a winded road. Now you're here. So maybe tell me, what's the next thing? What are you going to focus on now? And maybe what's the most pressing challenge you're currently solving?
Yeah. So right now I'm starting to focus more and more on Holonym and identifying kind of really great use cases, both within science and without, for zero knowledge technology, which I think could be incredibly important for society. At the same time, we're also further decentralizing the work that we've started with OpSci and looking towards using Holonym as kind of a base layer to build a distributed, professional, scientific society that's on-chain with portable academic identities and reputations that are linked reversibly or bidirectionally to off-chain academic web services like ORCID, Figshare, Open Science Framework, GitHub, you name it, and on-chain decentralized science ecosystems. So these like web native, Web3 native, like DeSci nodes, permissionless journals, data marketplaces, and basically building this bridge that allows scientists to make the best of both worlds, right? Because there's an emerging ecosystem that might allow funding to come in unparalleled sums to fund specific scientific endeavors and projects. And one thing with Holonym that we think makes that we think it makes possible that wasn't possible before is this idea of linking off-chain verifiable impact, right? So publishing reproducibly, using specific data standards, executing machine readable, basically open science practice, and linking that to on-chain records associated with that identity, that it can appear in impact marketplaces where funders that are seeking for specific types of metrics or specific types of outcomes that they can verify can help support and continue that work. So if I had to wrap up quickly, I would say the role of identity in creator economies where privacy is guaranteed as a right, and thinking about how we can build autonomous communities where science itself is the objective function of the protocol.
Very interesting. I'm very excited to see where you go, Shady, from here. Definitely a very challenging and interesting, well, all the worthwhile problems are challenging. So definitely, excited to see where you go. But curious, Carla, what are you going to think about or do differently after this conversation? What's your verdict after this?
Yeah, so I think I'm going to think more about zero knowledge proofs, because now I got a bit of an explanation and I totally see the value in it. And I think there's so much we can do with it. I just don't get it. So I think what I'm going to do is going to research it and try to understand how it works so that I can see how it can also help science.
Definitely. One of the things that that's definitely inspiring for me to look into as well, because I had heard the phrase, and I'm glad, Carla, that you double-clicked on it, expanded a bit, but the similarity with differential privacy and different types of encryption that we do is definitely interesting and a good starting point for me and probably people who are coming more from the machine learning side of things. I think coordination, you said something very interesting, which was software is also eating science. So I'm excited to see more software in science as we go forward. So thank you so much for spending time with me and Carla today. And this was a very fun conversation, and hope our audience has also learned something and joins us next week for the next episode of Deep Random Talks. Thank you so much.
Thank you, Shady.